Hello and welcome to the mini test solving for the lecture 26 Introduction to Integrals. So here is the mini test for those of you who want to solve it, and for those of you who came here for the solutions, let's jump right ahead into it. So for our first question we had to answer what does an integral represent. So a bit more theoretical question. We were offered 4 possible answers, so I'll go through each and every one so we can determine which is the right one, but also what the wrong ones really are. So for the first answer is the slope of the curve. We remember from the lectures before that's called a derivative. While this is the inverse of the integral, so no, this answer is not correct. The second answer is the sum of many very small contributions. To be fair, I could have worded it better, but it's fine, you get the point. And yes, we know that integral represents addition of very small values to precisely fit the area under the graph, or any other practical application, so yes, this is the correct answer. The third is the maximum value of the function. If we remember the last lecture, we had a rule for maximums to take the zero of the first derivative, insert its x into the second derivative, and if the value is less than 0, I think that's the maximum. So technically it's a use of higher derivatives. So again, not integral. And last is the value what the function approaches as x approaches infinity. Well, that's just the limit of a function when x approaches infinity, so we also know this one is not it. The correct answer being B. Simple. So, for the second one, we have to solve a given integral. First thing that we see is that it's an indefinite, so we must add a plus c at the end. Then we will use the table from the derivatives as well. We get the integral table next time. So, for e to the power of x, we know that the derivative of e to the power of x is e to the power of x. So now that we have an integral, we'll literally just use the triangle rule. So I rewrite that one as dEx equals ex dx. So to get the right side ready for integration, now we just like with logarithmization, we integrate both sides. Because I have a differential here, I have a differential here, we can integrate both sides because I multiplied by dx, right? So we integrate both sides. Because all we need for integrals are differentials, and you can cancel them out, and that something remains as the result. And please don't tell mathematicians I just said it, because, well, that's how physicists explain it sometimes, just like how when you have a differential and a derivative, you can cancel them out, but we'll get to that. But yeah, so we have an integral of just a differential. That is the function itself. So like, on the right, we see we have the integral we started with, and on the left, we could rewrite that e to the power of x as some a, so like this. So we would have a sort of differential of a function. So this behaves similar to dx, because x in itself is a linear function. So the differential of a simple function, if we integrate that, we get x. So if we integrate a simple function, whatever function it is, as a, we get a, like the function itself. So if we have differential of e to the power of x, this is a function, we get the function itself. So, kinda? Yes. Basically, e to the power of x plus c is the result of integration. So that's also our result. Don't worry, we'll get that in tables next time. Now for the third one. So for this one, we need to solve the integral here, and then see if we can write the g of x to match the form of the result of integration, and determine if we can what the constant would be. Sounds complicated, but it isn't that hard, so let's solve and see. So we'll start with the integral and use the inverse of the power rule to increase the exponent by 1, then divide the term with the new exponent. So get x to 3 divides by 3, x to the power of 3, plus c, of course, because we can't forget the constants. Now let's see if we can write the g of x as some x cubed that has a constant added to it. First, I'll multiply both terms by 2 to solve the brackets. Now I'll cancel the 2's in the fraction, and I'll multiply the x's together, basically simplifying, and I get x cubed plus 2 times square root of 2. And this part represents the constant because this is the same, and this is what parses a constant. So as it doesn't include the variable, we can write that as a constant, and we can say that yes, it does belong into the same family. So this kind of approach will be useful in physics when we logarithmize some formulas. and then linearize them. But don't worry, we get to that in a few years. Yes, actually next year sometimes. Anyway, that was it for today. Thank you so much for tuning in. Hope everything went well, and I'll see you all next time. Bye!